So, good morning again. My name is Arturo Bacco. I'm a PhD student from the University of Salerno. And my research is about thermostructural analysis of residual stresses in dissimilar welded joint, cast iron, and steel. This is a part of PRIN, is a project, PRIN 2022, in which the task for University of Salerno was to analyze the hybrid joint between the dissimilar metal materials. This PRIN is with the University of Padova, University of Pisa, University of Cassino, and the University of Ferrara. When structures are manufactured by welding, we have a rapid thermal expansion followed by a thermal contraction. These generate inhomogeneous plastic deformation and also residual stresses. The presence of residual stresses can reduce the performance of welded structure. Moreover, tensile residual stresses can be a source of cracking and fracture in the welding. It's practically impossible to have a complete distribution of residual stresses using an experimental technique. So, for this reason, the numerical model are often used to evaluate the residual stresses. For our analysis, we chose to use a decoupled analysis, to reduce the computational cost during the analysis. So we first of all created the model with the mesh. After we performed the thermal analysis to obtain the temperature distribution that we converted in thermal load, and used them as input for structural analysis to obtain the residual stresses. The technique that was used to simulate the welding process was the Birth-and-Death technique. It's a particular technique that requires that all the elements must be created also before welding, but also the element of the welding bead. But the element of the welding bead before welding are deactivated, multiplying their stiffness by a severe reduction factor. And then, during welding, to simulate the welding process, they are reactivated step by step. First of all, for the thermal analysis, we needed to evaluate the heat input for unit of length as a product of the efficiency, depending on the welding process, in our case 0.8, the welding voltage and welding current divided by the welding speed. If we multiply this heat input for unit of length for the length of the bead, we can obtain the total heat supplied during welding. This heat is also equal to three parts: the sensible heat, latent heat, and other heat on body flux, for body flux. Our components, when are reactivated during welding, are reactivated at liquid temperature. So, for this reason, in our model require only we must apply in our model only other type of heat input, so the input of body flux. And if we want to know how is the heat input for the single components, we must divide the heat input for the total model to the number of the components of whole welding seam. During an analysis using a FEM model, the energy can be supplied in two different ways. For example, first way is using an heat flux for unit of surface, or, as in our case, using a volumetric generation of internal energy. For our thermal analysis, we used as boundary condition only convective heat loss and the radiative heat loss that we converted in a convective part. For structural analysis, the rate relation between thermal stress and the strain is described by the following equation. We studied two different cases. The main scope of our research was to analyze the residual stresses in a particular joint, a circular fillet weld joint. But we considered that it's very difficult to validate the model using this type of joint, to make the analysis on this type of joint. So for this reason, we welded a butt weld joint for the evaluation of the weld joint quality, to validate the welding process, and also to for the validation of our finite element model. The material that we used in our particular application are two: a classic structural steel S355 and a spheroidal cast iron GJS500-7. For our thermal analysis, we needed in input the welding parameters that come from the real welding process, the model with the generated mesh, the thermal conductivity, and the specific heat at different temperature. In this slide, I summarized the thermal property that I used in my model for steel and the cast iron at different temperature. And for structural analysis, we needed in input the temperature distribution, as I told before, converted in a load. Stress and strain curves at different temperature, Poisson ratio, Young modulus, yield stress, and thermal expansion coefficient at different temperature. These are the mechanical properties that I used for steel, and these are the mechanical properties that I used for cast iron at different temperatures. To weld the butt weld joint, we machined a big groove with these sides. All the process was completed in two passes with the welding parameters that I summarized in this slide. During the welding process, we acquired the temperature using 6 thermocouple, 3 for each plate, at different distance between from the center of the welding bit, the center of welding bit. And in this slide, we can see there are 6 cores, 1 for each thermocouple, of the temperature during time. Each course has 2 peaks that corresponding when the torch is near the thermocouple during welding. After the welding process, we wanted to evaluate the quality of our welded joint. To do this, we performed a radiographic analysis. We can say in this radiography, no particular defects are present. We can appreciate the 6 holes in which for the thermocouple, and the different color of the welding bit and the 2 plates, depending on the difference of density of steel and cast iron. After we performed the macrographic analysis to evaluate the different zones into the joint, to measure the thickness of the 2 passes, and also to search some defects inside the joint. But how we can see, also in the macrography, no particular defects are present. On the same sample of a macrographic analysis, we performed the hardness test to evaluate how the welding process changed the hardness of the base material during welding. And we found a very, very high peak in the heat-affected zone at the side of cast iron. For our numerical model for the butt weld, we created a 3-dimensional model with hexahedral elements with 8 nodes, and 1 DOF for each node during the thermal analysis, and 3 DOF for each node during the structural analysis. This is the temperature distribution for the case of butt weld. This is the first pass. And we imposed during the 2 passes an interpass time equal 120 seconds, corresponding to real time during the two passes during welding. So, to validate our thermal analysis, we made a comparison between the curves from the thermocouple, the temperature acquired by thermocouple, and the numerical one. We can see we have had a more or less good accuracy, especially when we are near the welding bed. So when we made a comparison with the thermocouple near the welding bed. After we wanted to perform another validation, we made a comparison between the size and the shape of the zone into the joint with the numerical one. To do this, we compared the macrography and the numerical model, and we can see we have had the same shape and the same, more or less, the same size of the zone into the joint for both of the two passes. For our structural analysis, as boundary condition, we used boundary condition or rigid body constraint at one side of the welding bed, and at the other side, we used constraint due to welding, as in the real case. To validate our structural analysis, we made a comparison between displacement along the z-axis. We measured it using experimental using a CNC machine, and how we can see our model had an error of 9% at the side of steel and an error of only 9% at the side of only 3% at the side of cast iron. This is the stress distribution for a transversal path in the middle of the welding bed, and this is the longitudinal stress distribution for the same path. How we can see we have had a jump when we come from the steel to the filler material. This because we simulate the filler material as cast iron, so with the same property of the cast iron. This is the stress distribution for a longitudinal path in the middle of the welding bed, and this is the longitudinal stress distribution for the same path. For fillet weld joint, the welding process in this case was completed in 3 passes with these welding parameters. And the 3-dimensional model more or less was created as the previous case. So it's with the same elements and the same DOF during the analysis. This is the temperature distribution during first, second, and third pass. We used an interpass time equal to, in the real case, to 30 seconds between first and second pass, and 90 seconds between second and third pass. As boundary condition for structural analysis in this case, we used only the rigid body constraint. And the result of the structural analysis on the fillet weld, how we can say in this slide, we evaluated the axial stress, the radial stress, and the hoop stress in a cylindric system of reference with the axis corresponding to the axis of the tube. And we can see that the maximum value of residual stress was founded corresponding to the node between the first and the third pass. This is for a path on the tube, while these are the residual stresses for a path on the flame. We can appreciate how the residual stresses go down very fast when the distance from the fused zone grew. In conclusion, we can say that the numerical, the butt weld joint was very useful to validate our model, to verify that the process, the welding process, the real welding process that we were using were good. And also, this made it possible to evaluate residual stresses even in more complex configuration, as the configuration of a circular fillet weld. So, thanks for your kind attention.